speaker is İlkay Altıntaş, who was served on the committee that produced this report, and is a research scientist at UCSD and involved in some really ambitious projects that both make use of and contribute to this ARW vision.
Thank you, Dan. Thank you, and I'm really happy to be here in person. And I think some exciting conversations we had, hope we can continue them. I'm going to talk about two parts today.
Is your mic on?
It is on. Can you hear
okay.
me?
Yeah, okay.
Okay, perfect. I'll talk about two things today. I'm trying to get this one to work. Okay, perfect. Sometimes the mouse is not on it. So, by the way, I'm from San Diego Supercomputer Center at UC San Diego. I've been there the last 22 years. And also most recently, we have a department campus-wide without a dean called Data Science Institute, Halıcıoğlu Data Science Institute. And these two, I think, show where I cut my teeth in cross-disciplinary collaboration. So SDSC has, going with Alex's talk, actually an award since 2015 called Pi Person of the Year. So that shape, remember? And I was the inaugural recipient. And when I received the award, why? Because I'm round? Or, there is actually really symbolism to it, right? Because your both legs are in different parts of science and technology, and you're applying it. I think if you go back to Alex's talk, going from I to T to Pi takes a culture. And these two environments gave me that culture, and this whole colloquium, I think, is about that culture, and I'm seeing it here. So congratulations, Jing, first of all, and everyone here for creating and mentoring that culture. I'm a division director also at SDSC for cyber infrastructure and convergence research. Again, convergence research, I'm going to talk about it again. But it's driven by a societal context, right? This is multidisciplinary, cross-disciplinary science applied to a youth-inspired challenge. And there are specific cyber infrastructure-related challenges within convergence research. So in the division, all of our researchers and students work on problems at the intersection of cyber infrastructure, machine learning, data management, and also that societal use-inspired research. And my own research group is Workflows for Data Science Center of Excellence. And later on, you'll hear about the Wi-Fi Lab, which was an extension of the Word Center. Our mission there is really to develop methodologies and tools and formalisms, of course, on the research side for collaborative, workflow-driven science, for teams to work together to solve questions. So, focus on those questions, not the technologies, and really gather requirements from those problems has been our culture, and that's the first thing I'll ask my students in a way, how do you actually apply that? Right? So there is enough problems at that intersection that it's been very fruitful. So when I think of all of these, it gives us a pretty broad application context. And over the years, these applications related to big data, computational science, data science, all those things that, as buzzwords, we hear a lot, right? Internet of Things these days. But those are the problems we solve, and they have a context. So what's that application context? The first one, which convergence research actually came out of that context as a national priority for National Science Foundation, is complexity. We are at the age of complexity with complex societal and research problems to solve. And these are the grand challenges that Dan was referring to as well. Right? These are economical challenges, environmental challenges, public health, we all experienced and just heard a great talk related to it. These are really, really difficult to solve alone. We'll have to collaborate effectively. And of course, we'll apply advanced computing and data technologies to them. But a big part of it is collaboration, and that led to NSF's big idea of growing convergence research. How do you grow convergence research? What does that mean? There's a disciplinary research, which is very important, multidisciplinary research that, still groups are working towards a common goal, but separately. And when we talk about cross-disciplinary or interdisciplinary research, there's a problem everyone is solving together. And the convergence part of it is, how do you apply and actually ensure the use of that solution at scale in the societal context? What is the use-inspired platform or solution that's helping others? And how do we define the value and definition in general of it? And how does that happen? Right? In the cyber infrastructure world, there's a little bit of a cookbook in a way. We have part data management, part computational science, part data science these days with the AI integration, and advanced infrastructure. And generally, there's a method to madness to bring these together, and the experts working in those areas know how to put expertise together to solve that problem. But what problem they are solving, how are they collaborating as a cross-disciplinary team, is a culture of its own. And these days, people come together and there's data available, or there's like 15 years of Polish PhDs available, for instance. And then there's some translation of that into innovation as a group, and that gets applied in the scientific, societal, or educational context. So that's the impact of the work. But how do you go to something impactful? We need to think bi-directional. That's the convergence part of it. You actually run workshops. You have interviews with people who actually need these solutions. You go to industry, you go to government collaborators, and learn from that practice what can be use-inspired here. What is it? What is the art of the possible that science and technology can provide? And what is the workflow boundary we can push so we can move a knob a little further? Right? Moving that knob, what's that knob? That's the convergence research part. That's the use-inspired part. And this also comes a lot in the context of actually journals, new research areas. One of these is defined as translational computer science. If you're interested in this area, there are some early examples in the IEEE Computing in Science and Engineering, edited by Manish Parashar and David Abramson. And I think there we see examples of how do you take computer science from lab to bench, so to say, this translational biomedical context applied to computer science. So there is some methodology there. But again, translational computer science, in a way, isn't convergence research. You're still translating, but not with that societal context. So these are the things that I think our discipline is trying to embrace, that complexity. And in the heart of that is collaborative teams and thinking, right? That culture. So when we think of scientific process and workflows, then one of the things we need to do is think in not just workflows, but team flows. How does the teamwork flow? How does the collaboration flow? And what are our metrics for that? And do we all mean the same thing when we say delivering an expectation? Second application context, like we heard, we are in the age of big data and AI. And AI integration of applications at the digital continuum comes in pretty much every problem you pick from a mix of them. And what that typically means is there's some data, there's some sensors or things, Internet of Things, like instruments, big and small. And then it goes through a data management and AI loop to generate knowledge out of that, or they generate intelligence out of that. There are multiple purposes for AI within these contexts. And that gets applied to, in the scientific domain, modeling and simulation, or experimentation like we've seen, or synthesis, you name it. But there is this going back and forth with the modeling and simulation and data. And data starts at the source. We can't just take data halfway. without understanding how much we can trust the source and do something with it. So there's a lot of challenges there in terms of trustworthiness, ethicalness, privacy, accuracy. Those all require us to understand the data before the AI. We can't think AI without the data. But then this requires some computing, and turns out the computing challenges on one side of this big data to AI to modeling simulation is different than the other side. Traditionally, we've done the right-hand part of it, or downstream component of modeling and simulation, and with supercomputers. What that means is we used high-capacity computers with a lot of flops to do big computations. But when we think of data, or big data, or IoT devices, these are actually capabilities that integrate some form of computing. So we heard from Alex, for instance, link the telescope to an FPGA. That's a capability and very specialized to a certain type of data stream. So it's not replaceable, or it's not just scalable the way you scale supercomputing. So these came out as processing units, like the PUs in front of GPUs, CPUs, and many different types of it. Tensor processing units, for instance, is used a lot in deep learning, but also as platforms for what we refer to as big data. These are different types of data than relational data. There are different challenges from its volume, from its structure, variety we call it, from its veracity, or how data flows, its speed of ingestion that's needed for this type of data. So, and some requirements related to, let's say, privacy. Edge computing comes in the picture there, and also bandwidth and other challenges like latency of data can be answered by edge computing capabilities. So when you put these together, you have a very heterogeneous picture. And composition of all of that becomes a typical problem when you're trying to solve a problem as a team. And most of that expertise in those capabilities lies in different people. One person won't have all of that expertise. So in the report, one of the things, there are many other points that was captured is this: evolution of applications with AI, because workflows are the integrators, that composition entity, and it sort of gives us an opportunity to think in that process and AI's role within that process. And there are many interpretations to it, and the examples in the report gives various examples from different perspectives. But I think a big part of this is also the teamwork, that team flow component, and also open science. We heard really articulately from Alex why open science is important in this context. And this continuous integration and dynamic behavior of using a service when you can, based on data availability, based on emerging need, both within science and society, all of these, or in teaching practices, all of this requires now to look at systems as not just providers of a service, but providers of an ecosystem of services that can serve these different needs. So, and services that we are integrating. So that seamless integration is one of the things then we need to get from our AI sort of integrated world. Third context, I already, I think, made this point a little bit, is the many systems. We are in the age of many systems. What we mean by this, if you look at actually HPC Wire, which is one of the main publications related to computing, scalable computing, you see these different flavors of systems. You see systems that support some AI capabilities with specialized processors that NSF funded. There are 4 of them that was funded in the first generation of them. They all have different sort of processors in them to do specific things better. And then if you look at data components, we have, smart data and networking capabilities that actually link these systems in a lot more analytical ways than we could before. And then we have this concept of composition or composable systems that help us to pool together these resources and put them together as services or capabilities, as I was talking about, to many applications. So when you look at all of these, then they're actually driven by the requirements of the problems we are solving. They're data and AI integrated, they are heterogeneous, and they require collaboration. And existing systems we have right now give us data in terms of storage, data and knowledge management on top of that storage. So not just hardware that you have object storage and you keep it there. There needs to be some data management system to get the data from there and link it to an analytical environment. We have the continuum from edge to cloud to HPC. HPC actually in the DOE world and in the exascale these days. And high-speed connectivity. We are talking about 100 gigabit disk-to-disk connectivity at times that are programmable. So software-defined networks is a part of that. And the growing needs that applications require from these systems is how do they work together? How do they interoperate when I want to use two of them at once? Or how can I interact with them when I'm using an analytical application? How do they scale? When my application requires more resources, can I get more resources transparently? And are they black boxes or are they gray boxes? Can I get some performance measurements so I can actually predict and provision what I need and when I need? So that also points to the composability, because when you want to put multiples of these together, interoperating systems, are there composability approaches to them? So, and that is the main point I'd like to make actually today is there are applications that need this strategic ecosystem thinking. Because when we think of simulation and AI coming together, those are different services that run in different ways with different requirements from data systems around them. And we need to be able to integrate them. So without that strategic ecosystem level thinking, we won't be able to use them as effectively in a way that we can repeat. So coming back to it then, that application integration that I was talking about, systems, data and knowledge, artificial intelligence, and modeling and simulation. So that's another way of thinking of these. They have some integration requirements. One is that dynamic composability. Can we as a team come together, build our bits wherever we want to build them, and then put them together as a solution, step by step. And the fire example I'll give later has that example. The other one is, can I, as a team, use that dynamic service and in a way that enhances my teamwork? So the actually platform that I'm using helps me to make my solution more responsible. If there are privacy needs, does it help me to preserve it? Or does it give me measurements of uncertainty as I go, as a data system? And this doesn't exist. In today's systems, no cyber infrastructure framework will actually give us this effectively, that we can make sure the environments we build and support make science more responsible. So it's really left to the individual developers building a solution, individual teams building a solution to ensure that. When you put these into an architecture, dynamic composability these days comes from these containerized approaches. Systems are containerized. There is a management framework like Kubernetes for that. And on top of it, there are services that run, like microservices, that run in a containerized fashion on these systems. Team integration comes from being able to, as a team, have access to the data lifecycle management platforms, from active data repositories, long-term archives, knowledge network that I can fare data, like find, access, interoperate, reuse data through. And then also workflow systems that help us integrate these services. And that workflow system can be in the form of an individual Jupyter notebook that integrates these things, which doesn't give us much capabilities on top of that, but there is at least a record. And also full-blown workflow systems that gives us a little bit more around performance management, provenance management, and things like that. But then there are the blue bits. That's the effective collaboration and responsible AI parts. How do we couple team science, make that science reproducible, responsible, and also apply it in a use-inspired context? If you put them all together, it makes a complicated thing like that. And then if you simplify it a little bit more, we are talking about, again, that convergence of the blue with some layers of compute, composition, service applicability, and data management. And the research bits that's needed to be bridged for us to get there effectively are in dynamic measurement and provisioning resources, being able to create plug-and-play services that will have the necessary quality of service when you're actually using them in the context of sustainable solutions with the cost associated to it, because sustainable means we need to understand the cost of it and who would, in the long term, actually be responsible from the management of it. Something I do in experimental fashion. Can I move it to a cloud platform? Is it cloud compatible, for instance, comes to mind in the simplest form of that. And then running across many systems, that capability-based integration. It's not integration of running one service on one computer, but running a service on any number of computers that I can run it. So if one is not available, I can run it on the other one. If there's a reason, if my data is there, I'll move my compute there. We can make those decisions if we think of services as capabilities, not executables running on a specific platform. And then improved FAIR capability, and I say FAIR, findable, accessible, interpretable, reusable. These are great concepts, very useful to get the point across, but fair and responsible, right? Fair and factful. These are actually almost as important as making it findable, because if we make it findable, but in an irresponsible way, then we'll start having challenges related to that as well. So some examples of composable systems, what are they? Expanse is an NSF-supported supercomputer, and it's generally SDSC prides itself in supporting computers for the long tail, so small and big computations. So something that requires 1,000 nodes is as important as something that requires 10,000 or 100,000 nodes, that means. And we can go up and down in the use of these clusters. And composable systems is one of those specialized capabilities that helps use of the supercomputer itself to pool it as a containerized Kubernetes computer and federate it with other types of machines of that part. What this means is the scheduler is normally would be the Slurm, and you would get on a queue to execute something. Whereas in this world, you're actually donating some of the nodes to pool them together as a dynamically available cloud-like resources. And through the federation of that with many other specialized nodes, you're creating a heterogeneous supercomputer out of that pool. And this was inspired by the National Research Platform. It was the brainchild of Larry Smarr, and this was built on top of a really capable 100 gigabit disk-to-disk network with gaming GPUs to do big data training and inference. And that itself enabled many of us to build AI capabilities or services like machine learning, big data services that then be coupled to simulations over time. And it started small as an experimental computer scientist resource. It grew from that Pacific Research Platform and Nautilus into a national platform that connects now many nodes that are donating GPUs, FPGAs, and other types of specialized nodes to this environment. So when the users come to use it, they can select what kind of node they need. And the simplest thing they can do is put a Jupyter hub and a notebook on top of that. So you can actually use the resources through that pool that you selected that fits your application. So a little bit more complicated concepts maybe, but we need to embrace that type of complexity and not be scared of using these different nodes if that's the best way to do that. So how Expanse works, the first federation example in essence in Expanse was that Kubernetes pool part of Expanse was federated with Nautilus, and we were able to overlay applications on top of that. And I'll show you some examples of those applications. And of course, you can make that pool with different topologies. You can control with one node. There's the Admiralty software was used as the federation platform. I just left it there if you'd like to read more about Admiralty itself. And then the other composable system on top of these is edge. What happens at the edge? And some of us, led by Pete Beckman, built this AI at the edge computer, Sage. Sage is a combination of sensors and AI accelerators deployed in the wild with some topology to it. And it enables, in a virtual fashion, building AIs that could be deployed to run on those Waggle devices at the edge to process the data on the edge that it's being collected. The biggest difference here that I'd like you to notice is there is a virtual platform that you're building things that you can analyze and infer with. The community of researchers are building this. And when needed, you can reprogram a device in the middle of nowhere to run that AI. Basically, you're scheduling an AI in a very small platform. There are very different scheduling challenges, right? You're basically scaling it down in the first place. But also, what happens if two people want that? You don't have enough resources. So that's a different type of scheduling. What we were able to at least do is compose Sage, that small environment, and full Kubernetes is for clusters, it's good. K3s is a lighter version of Kubernetes that enabled us to run those edge devices as also containerized bits into this federation. When we do this, now we have Nautilus as the head of the topology, sort of, it's like the main manager of it. There's Expanse, which is HPC. Nautilus is like gaming GPUs and FPGAs or more specialized resources. And then there's the edge resources of different accelerators. They become resources here. And I can get which ones, I can deploy a whole Jupyter platform on top of that and just code to execute things on it. Right? That makes it a lot simpler. Compute part of it is maybe simpler, but you need a data fabric on it. And a huge part of the national cyber infrastructure community is trying to solve that. How do you build now data systems to bridge that and make sure they can be federated into this picture? So that's the backdrop. And in the next 10 minutes, I'll try to give you some examples. Yeah, I'll try to leave some questions. Yeah. So how did we apply these, first of all, to fire? And why is fire problem important? Because it's a crisis. We are in a crisis. We have these big mega fires, and there's nothing natural about them. Fire is very natural. It has to happen on a regular basis in low intensity context. So nature actually needs to clean itself once in a while, give new life to things. But the way we managed existing fires and the way we are building our communities around the wildland, it's called the wildland-urban interface, we had to manage fires differently for good and bad reasons. And also, we increased human activity in the wildlands, so we increased the risk of wildfires. But at the same time, since we are suppressing a lot of fires, we have a lot of fuel. So it's kind of counterintuitive that we don't have enough fire in the landscapes when all we hear about is fire. So that's called a fire deficit. We are in a fire deficit. That means we are paying the debt we didn't pay in the last 100 years. And of course, we are in a drought, and climate is changing. So we are in this perfect storm, and we need to find a way to get out of it. And fire science is actually a really vibrant area. Lots of fire sciences, lots of approaches, computational fluid dynamics-based models, point progression PD-like models. There's AI-integrated models. A lot of people are trying to model the behavior of the fire. And all of these are actually, this is my 10-minute alarm. All of these are really important pieces of work that will solve parts of the picture, because we can't get out of it using one solution. There are going to be many use-inspired solutions to help us mitigate from them, to help us respond to them, to help us prepare for them, to help us recover from them, right? There are different parts of the solution, and within that, there are many use-inspired challenges. But these next-generation fire prediction behavior understanding models also comes with requirements on data and also learnings from data. Compared to 20 years ago, we have weather forecasts that's more detailed. We have weather sensors, stations out there, that gives us detailed data. Satellites give us much more higher resolution, temporally and spatially, about the environment. We have remote sensing through satellites and also using different types of sensors, and overhead sensing, LiDAR sensing, imagery, SAR, IR. These are different types of sensing capabilities that helps us see the environment differently through different bands. And we have much more detailed landscape data. We have better historical data. So the data is better and more detailed. So we almost have too much information. And how do you get from that data-rich environment to a knowledge-rich environment? This was a gap. When we started, actually, there was no way of bridging these silos and making them accessible through a programmatic interface in a way that gives meaning to those data sets. So that's through National Science Foundation. That's what we started about 13 years ago on building a cyber infrastructure. And that cyber infrastructure slowly evolved into a solution because word got out that we were doing fire modeling using real-time data. And in LA, from the mountain to the ocean, 2 hours. If there's a fire in the Hollywood Hills, you have 2 hours. You need to initial attack that, like, with all you got. Otherwise, you lost the communities. So that dynamic information of real time, where the fire is going to be, who am I going to evacuate, that first couple of hours of the fires is much different than how you manage the rest of it. And in these wind-driven fires, it sort of defines the fate of that fire. Because once it gets out of hand, you're going from an ignition point to a bigger, in the next half an hour, to an unmanageable domain. So you need to hit it when it starts and in the right direction. So FireMap has done that with real-time information that I'll show. And now we are going into more mitigation with Vern Pro 3D, which is our prescribed fire optimization tool. But this all built on that composable systems that I was talking about, with a data and model commons that bridge these data and models through an AI gateway that we can learn from data and constantly making sure it turns into a service that an integrated workflow can take advantage of. And when you build these things, the model commons and data commons, within that, of course, there's an execution environment like the Jupyter Hub I was showing you. But also, there are things like ontologies and knowledge management frameworks, knowledge graphs that we need to take advantage of. And that execution environment also needs to keep it semi-responsible, at least at the moment, to make it transparent where it came from, reproducible, and all those provenance details need to be there. And the data that we archive, we make it to a point, as much as we are allowed to, openly available with DOIs, the digital object identifiers. So once the data is used, users can be sure the data is there, and they can always refer to it for their analysis. So then to solve a problem like that big architecture I was showing you, this is the use-inspired version of that. You need a data system. On it, you need a system to make the data higher value. On it, that valuable data set as a service needs to be a part of a fire science workflow. And then that gets integrated into a use-inspired platform. And this slide, I didn't mean to explain this, but this is actually what's using that composable infrastructure. And it's deploying community-developed tools like X-ray and PanGeo on top of that composable infrastructure, so we don't have to repeat what the geoscience community has done. They were developed at NCAR, these particular technologies. So then focusing on two ways, right? There is the response, which is the reactive mode, and that's the fire map approach. There is a fire happening. How do you characterize that fire environment? It ignited, you get that ignition point. How do you use cameras? How do you use satellites and reported ignitions to make that ignition point more accurate before you start modeling? There's a whole fusion center we built with CalOES, California Governor's Emergency Services, to create that fusion center approach. And then human in the loop, you also keep learning about. There's a plane that goes up in the air that gives us more parameters on, the fire environment. So this constant characterization of weather, fuels, perimeter gets combined with an integrated fire model in the background. And humans actually are the safekeepers there. There's fire managers looking at the models if they could be shared, if they are realistic enough, because they know where the fire is being managed. And of course, in there, you can use many AIs. One I left for the slides is the smoke detection. There's a lot of people I know are interested in that particular area. And for that to work, we needed training data. So what we had done is we created labeled images for smoke. Now, if you're interested in it, FigLib gives you training data to develop more of these smoke detections, and they can be archived in the model commons. So that's how we plan to engage the community. And this slide particularly explains how Expanse, Nautilus, and edge detection on SAGE is integrated into that fire workflow. But when you're doing prescribed burns, it's a lot more complicated. We are going from a 2D fire model to a 3D one. I don't think I'll be able to run that. So you're actually going from 30 meter in 2D with the rate of spread to an environment that you have volumetric information and what the fire is doing in the environment. And since we are going to put fire on the ground, prescribed fire is a controlled fire that we are treating vegetation to remove it. You need to understand what's there. And you need to run many scenarios to understand how to run that. So 3D dynamic fire environment data. Suddenly we have all the more data and complexity. And then interpretability of that 3D model. How do we ensure that? This is what Vern Pro 3D is trying to do. Using that composable framework, I left this on the slide to see also how, Nautilus, Expanse, and cloud providers are coming together as an architecture. So if any of you are interested in it, I'd be happy to talk about it. But we start with the 3D fuel models, which are just 1 meter resolution, also just in 2D. They are 900 times more higher resolution. But then there is a 3D volumetric component of it that comes from things like LiDAR measurements. So if we continuously on-ramp, now we know what's there. We have a model that requires a little bit of an AI. We have a model that can ingest it into a fire model that can then turn that information into what burned. And how do we explain what burned? And how do we use that to optimize where and when to burn these fires? How do we help burn bosses planning these? How do we help them monitor it during the implementation? So there's a lot of explainable AI optimization, and also to make these runs cheap, physics-guided machine learning emulators needed to carry these to a societal scale. So that's the type of research we are doing. And SAGE, for instance, I'm going to come back to it. Why do we need edge? Because during the implementation of it, then for physics-guided machine learning, for instance, we need to collect data, so validate those. And this is an example burn that was done on a prairie, so a lot more simple than a forest. But we collected a number of data sets. So before that, there is this campaign of how we are going to collect that. And we used smoke detection and fire detection as an AI to deploy in that SAGE sensor during the day off, but you need to understand whether go, no-go decisions get made. And after, these need to be published as an open data set to the community so everyone can benefit from the learnings. So there are some ingredients here for these platforms to happen. I left them, some of them, but you see there's the data layer, compute layer, and the user-facing layer. We can't avoid that user-facing layer and web-based platforms. That's a lot of UI/UX expertise we had to build. That's something we didn't have before. We also had to build in social science expertise to bring in social sciences to the team so we can effectively work in the societal context. But I want to give this as an example to once you start building a common environment that people can work through data, you can definitely enable better science, but you can bridge that science also in a lot more responsible way to solutions. And of course, the heterogeneity and composable systems are two things that we had to use in the background, hand in hand, to capture the complexity of the application and map it to the underlying infrastructure. And last thing I'm going to say is I'm not taking this as a simple, talking about these are simple things to do. We are still learning every part of it and running into challenges. Like Vern Pro 3D has 4 systems in the background. It's the 5th system that integrates this without the AI. And then there is the AI integrations that going into it. So that system integration, we thought we would be done in October. Today I got the note that it's done. So these things are challenging, requires incorporating a whole lot of people into it. So not turnkey functionalities yet, but I think we need to all push in that direction of how do we integrate data and meaning of that data with the rest of what we are doing. And you know, at the time that science is needed at the societal context more than ever, how do we actually deploy it? How do we build these things for deployment? So 5 more minutes, maybe.
Well done. So, let me put this on. That was a great talk. Here's what I suggest. We've got like 5 minutes for a question or two. Then we'll move on to Tapio's talk. And then I think we'll have 30 to 40 minutes at the end that we can ask questions of any of our speakers, okay? You know, I was thinking, particularly that prescribed burn system you're building. You know, we write our papers and we send them out and we hope they get good reviews and get good, you know, H numbers and all that. She's doing something where somebody's going to actually light a forest on fire based on her results, right?
No pressure.
Are they doing that yet?
We are demoing it.
Okay, that was fantastic. Thank you so much.